All right, 5.5. This section is pretty long. We're going to be breaking it up into 4 different days, but there's a lot of information and it might be different than anything you have seen before, or you may have seen some of these things in Algebra 2 if you took Advanced Algebra 2, or you may have never seen some of these things before. So make sure you are paying attention, taking notes, and asking if you have any questions. So the first thing is the remainder theorem. And that says if the polynomial f of x is divided by x minus k, so like we were doing in 5.4, dividing a polynomial by a linear factor, or just a binomial, sorry, not necessarily a factor, then the remainder is equal to, so remember how when we were doing synthetic division, we would end up with the remainder, which was that last number that you got. Then the remainder, that number is going to be equal to f of k. So if I plug in this number in for x here, that's f of k, but it turns out that the remainder, when you do synthetic division, actually equals f of k. So you always know what f of k is based on the remainder. Now you might be thinking, but isn't it easier just to plug the number into the function? Well, if I took away your calculator, you wouldn't think so, because then you would have to be doing, let's say, plugging this 4 in for x here. You'd have to do -3 times 4 to the power 4. Well, you may not even know what 4 to the power 4 is in the first place, so then you've got to do some multiplication there before you can even multiply by -3. And then you have to do 4 cubed here, and then multiply that by 15. So it's just, that would be actually a lot of work. Versus the synthetic division process that you just learned actually is a lot smoother and easier. And so we are going to look at how you can do so many different things with synthetic division. And so you need to be able to obviously do that. All right, let's see. So we just learned that the remainder is equal to whatever you would get when you plug that number in. So use the remainder theorem to find f of 4. So f of 4 is going to be the same thing that we would get if we did this divided by x minus 4. So we would put the change the sign here, put that in the box. 4. List out your coefficients, make sure there's no terms missing. 4, 3, oh, x squared is missing. Let's insert a 0x squared here. Maybe I'll write that below so you can actually see it. Okay. Adding a 0x squared there, and then we've got a 1, and then your constant term. Okay, so we're going to list out our coefficients. -3, 15, 0, -50, 25. All right. Drop down that first number. Multiply the number in the box. 4 times -3, -12. Then we add 15 plus -12, or you can say 15 minus 12, same thing. 4 times 3, 0 plus 12. 4 times 12, -50 plus 48, 4 times -2, 25 minus 8, that's not right. Okay, so this last number is the remainder, which is also going to be f of 4. Because we just divided that polynomial by x minus 4, this last number, your remainder, is f of 4. So f of 4 equals 17, assuming we did everything correctly. All right, let's try that again. So again, we are finding f of 4, so we're seeing what this would be if I divided by x minus 4. So put the 4, in the box. We're going to have to insert a 0x here. That's a missing term. 3, 2, no x. So we've got to insert that 0x. So -1, 8, 0, -63. Bring down your -1. Multiply 4 times -1. Add, multiply, add, multiply, add, just 1 left over. So this is your remainder. So f of 4 here equals 1. And that was a lot faster than if we had actually plugged in 4 here. -4 cubed, 4 cubed is 64, that's -64, and so on. You're just like having to do a lot of multiplications there. A lot of computation there. But the synthetic division process, pretty smooth. All right, so just so we have this down for sure, the remainder, when you do synthetic division, is the value of f of that number, which means it's the y value, right? So you're saying when x is 4, the y value is 1 for this polynomial. When x is 4 for number 1, the y value is 17. Okay. Now let's look at testing potential zeros. A zero of a polynomial function, f of x, is a number k such that f of k equals 0. That's why it's called a zero. It's where the function equals 0. And you also know that that is the x-intercept when you're looking at a graph. If it's a real 0, so it's not an imaginary number, then that's going to be an x-intercept on the graph, right? Because the y, you're saying the y value equals 0, so it's going to be an x-intercept. Now also, f of x divided by x minus k must have a remainder 0. So based on our remainder theorem we just talked about, this would also imply that if the remainder is 0, then this is a 0 of the function, or k is an x-intercept. Okay, so you're looking for having that remainder 0, and that means that that number that you divided by is a 0. Okay, let's try it. Determine whether the given number k is a 0 of f of x. So we're going to divide by x minus 2. So we're putting our 2 in the box, listing out our coefficients, inserting a 0 for that missing x term. Okay. Okay. Bring down the 2, multiply, add, multiply, add, multiply, add. All right, my remainder is -14. So f of 2 is -14, which means that 2 is not a 0. Right, because the y value is -14, which means it's not on the x-intercept, clearly. Okay, let's try number 4. So we're dividing by, this time you're dividing by x plus 3. So our -3 goes in the box. We list out our coefficients. Make sure you're not missing any terms. Not on this one. Okay. Try completing this synthetic division process on your own to see if you've got the hang of it. All right, so my remainder on this one actually came out to 0. So this means f of -3 equals 0 by the remainder theorem. Therefore, -3 is a 0 of f of x. Perfect, so that's what we're looking for. -3 is a 0. -3 is an x-intercept if you're looking at the graph of that function. All right. Number 5, we actually have an imaginary number here. So let's just see how this could work. You could plug k in for x and multiply, but let's just play around with synthetic division and see what happens. 2 minus I is what we're dividing by. And we've got 1, -4, +5. Okay, so bring the 1 down. 2 minus I times 1. Well, anything times 1 is just itself, so that's going to be 2 minus I. Then we add, so -4 plus 2 minus I. You want to combine like terms here, so that's -4 plus 2 is -2. There's nothing to combine with the -I, so it just stays -I. All right, now we are to multiply 2 minus I times -2 minus I. Those are actually conjugates, which you've seen before, but let's just multiply them out here. 2 minus I times -2 minus I. FOIL that, so -4 minus 2I plus 2I plus I squared. Now remember, I squared is -1, so this is actually -1. All right, so that simplifies. We've got -4 minus 1 is -5. My -2I plus 2I cancels. So this gives me -5. Now 5 minus 5 is 0, so my remainder here is 0. So what you're saying is f of 2 minus I equals 0. Therefore, actually that symbol means therefore in mathematic language. So therefore 2 minus I is a 0. It's not a real 0, it's a complex 0. And so it's not going to be an x-intercept because it has an imaginary part there. Is a 0 of f of x. All right. All right, page 2 of 5.5. We are looking at what's called the factor theorem. This says for any polynomial function f of x, x minus k is a factor of the polynomial if and only if f of k equals 0. So that's a common theme here. So just on the previous page, we were saying, okay, if I divide by x minus k, my remainder is 0, then k is a 0 of the polynomial. K must be a 0 of the polynomial. Well, don't we also know that if k is a 0, that implies that x minus k is a factor? And vice versa. Okay, so these two go hand in hand. All we're adding on here is saying not only is k a 0 of the polynomial, but we can also say that x minus k is a factor of the polynomial. And so let's see how this plays out in number 6. All right, so we're determining whether x plus 4 is a factor of the polynomial. So we're going to divide by -4. Well, I mean, we're going to put -4 in the box, but we're dividing by x plus 4. So we list out our coefficients. Don't forget to insert a 0 there. Okay, go ahead and do the synthetic division here. All right, now since your remainder here is 0, we know a couple of things. Based on what we just looked at on the previous page, that means that -4 is a 0 of the polynomial. Okay, so we know f of -4 equals 0. Therefore, -4 is a 0. But talking about the factor theorem, it means that x plus 4 is a factor of f of x. It is a factor. And we also know a couple of other things. So we learned that when we did long synthetic division in 5.4 that these are your new coefficients, right? Plus your remainder here. Well, if the remainder is 0, then when I divide out the x plus 4, what I actually get is 3x cubed minus, right, I go down by 1 degree, so it's going to be cubed instead of to the power of 4, minus 12x squared, plus 0x, I don't need that, plus 8. This is the quotient. So after you've divided out the x plus 4, you have this new polynomial, which is your quotient. All right, let's try that again on number 7. So we're checking to see if x plus 4 is a factor again. So we've got -4 here in our box. Listing out your coefficients. Don't see any missing on this one. Okay, now we perform synthetic division. Okay, be careful here because remember we are adding these two together, so that gives me -40. So my remainder is -40, not 0. Okay, and if it's not 0, then the factor is not a factor. So -4 is not a 0, x plus 4 is not a factor. So since f of -4 does not equal 0, right? Because the remainder was -40. And we know the remainder is equal to f of -4. Therefore, x plus 4 is not a factor. Okay. Now, the last thing that we want to look at is, we're going to do a little bit of that and then talk about how we can use synthetic division to actually factor polynomials. So you might get some polynomials like this one on number 8 that you cannot factor. You can't factor that one using grouping, and so you don't know how to factor this polynomial at all. But if you can figure out one of the factors of the polynomial and divide it out using synthetic division, then maybe you can factor it from there. So that's how this is going to work. On this, you're given one of the zeros. So it says factor f of x into linear factors given 5 is a 0 of f of x. So if 5 is a 0, then we know that when we divide, the remainder is going to be 0, right? And so let's do that. So when we divide, so again, if 5 is a 0, then we know x minus 5 is a factor. If 5 is a 0, x minus 5 is a factor, and when we do synthetic division, our remainder is going to be 0. All right, so we've got 5 and we're putting our coefficients. Okay. All right, so of course I got remainder 0 because x minus 5, they told us, was a factor. But not only is x minus 5 a factor, but now I have 6x squared minus 7x minus 3 as my new polynomial after x minus 5 has been divided out. So that means that I have this times x minus 5. F of x equals that quotient times the divisor, right? Dividend equals quotient times divisor. So now you have partially factored this polynomial. Now we're going to continue factoring it just using standard factoring methods. So we're going to factor this using grouping, or whatever method you use to factor trinomials. Okay, so I'm going to do that over here. 6x squared minus 7x minus 3. So I'm looking for two numbers that multiply to 6 times negative 3, which is negative 18. So I've got 1 and 18, 2 and 9, 3 and 6. Do this however you're comfortable. So two numbers that add to negative 7, 2 and negative 9. Now you can either use the AC method, which you're going to do x plus 2 and then divide by 6 because you multiplied by 6 at the beginning. X minus 9 divide by 6. So you can do that. We call that the AC method. Reduce the fractions and then bottoms up. Or you can use grouping, which is what I taught when we did factoring. So I would do 6x squared plus 2x minus 9x. So what you just did would you split up the negative 7x into 2x minus 9x, right? Because 2x minus 9x is negative 7x. Hopefully we've got the hang of factoring, but I know some of us need a review sometimes. And then we group. We factor out the GCF for each group. Anytime there's a leading negative, like in front of the 9 here, you want to make that part of your GCF. Okay, and now you've got these matching two binomials, 3x plus 1, so that's one factor. And then these two GCFs that you took out, 2x minus 3 is your other factor. Okay, so when I factored the remaining polynomial there, my quotient, I got these two factors. So the total factorization of f of x is going to be those two plus this x minus 5 that we already had. Okay, so I'm going to write that out. I had x minus 5 from the beginning. They told me that one. And then I factored what was left, 3x, and I got 3x plus 1, 2x minus 3. And so that is the linear factorization of our polynomial. Let's try number 9, the last one that we're going to do in this set of notes. All right, factor into its linear factors given negative 5 is a 0. So if negative 5 is a 0, then I should be able to divide x plus 5 out of f of x. Perfect, remainder 0. So your remaining polynomial is 8x squared, going down by 1 degree, plus 10x minus 3. Okay, now you would want to take that. Okay, remember this means x plus 5 is a factor. Now you want to take this, what's left over, and actually factor it. So use whatever method you're comfortable with. Again, that means that this times x plus 5 equals f of x. But now we want to take this and we want to factor it because we're trying to find linear factors, but this one would be considered quadratic. So we've got 8x squared plus 10x minus 3. So looking for two numbers that multiply to negative 24. Looks like 2 and 12 is going to do it to add to 10, so negative 2 and positive 12. Okay, I will group the first two. Group the last two, GCF for each group. You should always know factoring is going to come back up over and over again. Okay, so those are my two factors. Getting that 2x plus 3 from those two GCFs, and then the 4x minus 1 from those two factors there. Okay, so those are my two factors from my leftover quotient, but I also had the x plus 5 to begin with, so let's write out our final answer. I had x plus 5. Then I have these two factors that I just got from factoring the quotient. All right, and that's it for part 1.